Deep beneath the surface of the Pacific Ocean, a giant is waking up. It has no voice, no physical shape, and no warning cry. It does not crash through the forest like an earthquake or announce its arrival with the visible fury of a volcanic eruption. Yet, it possesses more kinetic and thermal energy than thousands of thermonuclear weapons detonated all at once. And right now, it is surging across the widest ocean on Earth at a speed that has left our most advanced climate supercomputers completely bewildered. For 3 long years, the tropical Pacific was quiet. It rested in a state of tranquil, icy neutrality, leading many to believe that our weather patterns were stabilizing. But in the early months of 2026, the deep-sea sensors began to return impossible readings. At first, oceanographers desperately hoped it was a software glitch, a calibration error in our marine hardware. Perhaps a cluster of automated buoys had drifted into a localized volcanic vent, or perhaps a telemetry error had corrupted the data packets sent to the satellites. But as the data poured in from thousands of independent automated profiling floats and deep ocean buoys scattered across millions of square miles, the terrifying reality became undeniable. We are currently witnessing the birth of a climate titan, a super El Niño so sudden and so intensely powerful that it is actively rewriting our fundamental understanding of atmospheric physics. This isn't just a routine shift in the seasons, this is a planetary realignment. But why is this happening now? What broke the planetary patterns we have relied on for generations? To solve this global mystery, we have to look hundreds of feet below the sunlit waves to a place where the ocean was quietly building a massive, highly volatile thermodynamic battery. To understand the true scale of what is unfolding in 2026, we first have to understand the normal everyday state of the Pacific Ocean, a system that acts as the planet's primary thermodynamic engine. Under normal conditions, a silent global tug-of-war governs our weather. Powerful atmospheric currents known as the trade winds blow relentlessly from east to west, from the cold coasts of the Americas toward the warm seas of Asia. This is driven by the Walker circulation, a colossal loop of rising and sinking air that spans the entire equatorial Pacific. These trade winds act like a giant invisible broom sweeping across the water. They literally drag the sun-baked warm surface waters of the eastern Pacific westward, piling it up around Indonesia. But there's an even deeper force at play here. Ekman transport. Because of the Earth's rotation, the wind doesn't just push the water straight, it deflects it. This deflection, known as Ekman transport, forces the warm surface water to accumulate in the Western Pacific warm pool. Because of this constant relentless wind pressure, the sea level near Indonesia is actually about 50 centimeters higher than it is off the coast of Ecuador. Think about that. The ocean surface is literally tilted. The Pacific is piled up into a giant watery hill of heat on one side of the planet. This displacement triggers a critical oceanographic process called upwelling. As the warm water is swept away toward the west, freezing cold, nutrient-rich water from the deep ocean rises to the surface along the South American coast. This cold water acts as a natural air conditioner, keeping the regional atmosphere cool, stable, and highly predictable. It also feeds the richest marine ecosystems on the planet, supplying vast quantities of plankton, anchovies, and marine life with vital nutrients. But this system has a dramatic breaking point. From late 2020 all the way into early 2023, the Pacific experienced an incredibly rare, prolonged triple-dip La Niña event. During La Niña, those trade winds don't just blow, they rage. They blew with hyperactive force, day after day, week after week. They push more and more warm water to the west, packing it tightly into the Western Pacific, like a spring being compressed under immense hydraulic pressure. What most people, including many policymakers, didn't realize was that the Western Pacific had become a colossal, overcharged thermal battery. The heat hadn't vanished from the planet. It was simply being forced downward, stored under immense hydrostatic pressure beneath the surface where satellites couldn't easily see it. The planetary spring was coiled to its absolute limit. It was a massive reservoir of energy, just waiting for the trade winds to falter. And in early 2026, the winds didn't just falter, they completely collapsed. When the trade winds suddenly weakened in early 2026, that massive towering pile of warm water near Indonesia had nothing left holding it back. Gravity took over. The thermal spring uncoiled with explosive force, but because of the rotation of the Earth, this warm water didn't just drift back slowly across the surface. Instead, it triggered an underwater phenomenon known as a downwelling Kelvin wave. Think of a Kelvin wave as an invisible deep-sea tsunami of pure thermal energy. Unlike a regular wave, you cannot see it on the surface with the naked eye. It doesn't crest, crash into foam, or disturb the ship sailing above it. Instead, it travels horizontally hundreds of feet down, sliding along the thermocline boundary. This is a massive pulse of heat, thousands of miles wide and over 100 meters deep, traveling across the widest ocean on Earth at a speed of about 2 to 3 meters per second. As it moves, it carries the kinetic force of a planetary rearrangement. As these Kelvin waves travel eastward, they act like a thick, insulating blanket. Under normal conditions, the Eastern Pacific is cold because cold water can easily upwell from the deep ocean to the surface. But as the Kelvin waves arrive off the coast of South America, they physically push the thermocline down by up to 100 meters. This suppresses the normal upwelling of cold water. The freezing nutrient-dense currents that usually rise from the deep are completely blocked, trapped beneath a suffocating layer of imported tropical heat. By the spring of 2026, these hidden heat reservoirs finally made landfall on the South American continent. When they slammed into the continental shelf of Peru and Ecuador, the warm water was forced upward to the surface. In a matter of mere weeks, sea surface temperatures in the Niño 1+2 region, the ocean waters directly off the coast of Peru and Ecuador, spiked by an astonishing plus 1.8 degrees Celsius above the historical baseline. Normally, the atmosphere and the ocean take months of gradual interaction to negotiate this kind of massive heat transfer. But in 2026, they bypassed the negotiations entirely. The system was in freefall. In the world of climate forecasting, there is a legendary, highly frustrating obstacle known as the spring predictability barrier. During the Northern Hemisphere spring, specifically the months of March, April, and May, the global atmosphere and the ocean are in a state of high transition and extreme instability. The coupling between them is highly volatile, making it notoriously difficult for even our most powerful supercomputers to predict how an emerging El Niño will behave. It is the meteorological equivalent of trying to predict the exact resting position of a spinning coin while it is still bouncing violently on a wooden table.